तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had discussed a variety of oscillators so far. RC oscillators, under this category we had discussed Wien bridge oscillator, phase shift oscillator. LC oscillators, under this category we had discussed Hartley Colpitts oscillator, okay, and also gyrator simulated oscillators. And crystal oscillator, we just mentioned at the end of the last class that the crystal can replace an LC circuit, because basically a crystal is a combination of series resonance and parallel resonance circuit, actually represented so this crystal has an inductor in series with the capacitor and a small resistance, and then a shunt with, of course this is not wantonly put, this is going to be the electrode capacitance here, right. So, and also the stake capacitance. It has a series resistance and a series capacitance and an inductance. And therefore, at the series resonance frequency is omega naught is equal to 1 over root Ls Cs, that is the series resonance frequency, and the parallel resonance frequency is omega naught is equal to 1 over root L. Across L you have Cs coming in series with C shunt. So, Cs C shunt, okay, we will put down this elsewhere. This is series resonance, this is parallel resonance, 1 over root of L Cs C shunt divided by Cs plus C shunt. They are coming in series. So, effective capacitance is that. That is the parallel resonance circuit. Parallel resonance. It can be seen that this is very nearly equal to 1 over root Ls Cs, primarily because you can take this out, the root of 1 by 1 plus Cs by C shunt. Right. This Ls Cs you take out, then divide by C shunt, okay. Because this factor is going to very small value, right. That means actually if you put additional C shunt, it is closer, right, to the actual. That means basically this ratio is very small compared to 1 by structure, okay. So, additional C shunt will again make it closer to this series resonance. So, this fact has made this very popular, because you can get a wide range. For example, when it is in series resonance, it is a short circuit basically. That means actually it is a small resistance okay, in series, that is RS. Okay. And a parallel resonance, it is going to be an open circuit. That means a huge resistance value, okay, which is Q squared times RS, right. Basically, the quality of this is very high. So, it is an open circuit. So, the impedance level can go from short circuit to open circuit around a small change in frequency. That small change in frequency depends upon this deviation here. Okay. So, you can see that this is a very versatile circuit which will act as capacitive or inductive or short circuit or open circuit around the same frequency. This is an important property in what we call now as frequency stability in oscillators. Let us understand this basic concept. What is frequency stability? The frequency of oscillation in all these oscillators, for example, in RC oscillators, is determined by the resistance and the capacitance this way. Omega naught is invariably equal to K by RC. You need a minimum of 2 RC networks, 2 time constant, in order to make any oscillator, not single. With single time constant, you cannot make a harmonic oscillator, because second order is the basic requirement of second order differential equation. So, 2. That means, basically this is going to be some K divided by root of some R1, R2, C1, C2 for any oscillator, K differing depending upon the type of oscillator. Okay. That means, sensitivity of omega naught to R1, R2, C1, C2, they are all same. Okay. Sensitivity in this case is equal to half. What is sensitivity? Sensitivity is defined as omega naught to R1 is defined as delta omega naught by omega naught for delta R1 by R1. Okay, this is the definition of sensitivity. What is the change, percentage change in frequency for a change in the component value? That is defined as sensitivity. Okay, percentage change in the frequency for percentage change in the component value, that is defined as the sensitivity of omega naught to R1. Similarly, sensitivity of omega naught to R2. Okay, this R2 will come here, delta R2 by R2. Now, this one, if you determine for this, will be equal to minus half for all these components. Okay. That is because there is a root coming. Okay. So, you will see that sensitivity is going to be minus because it is coming in the denominator. Okay. So, whenever anything comes in the denominator, we have negative coming, that when that component increases, this other parameter decreases, right. That is indicating negative, and it is half. You can see this. Therefore, the sensitivity of passive component here for LC oscillators is also the same, half, minus half, L and C. So, it is the same R1, R2, C1, C2, okay, L, C. So, these are all. So, sensitivity to passive components remains the same in all these cases. Okay. Ls and Cs also is half, except for C shunt it is not sensitive at all. This you can see, right. For sensitivity of omega naught for C shunt is very nearly 0, right. So, I am discussing this passive parameter sensitivity in order to illustrate that apart from this passive parameter sensitivity, it is bound to be sensitive. Okay. There is no way avoiding it. What it means is, if resistance varies with respect to time, temperature, etc., the frequency is going to drift. But therefore, we will make sure that these resistances are chosen in such a manner that there is no drift in the frequency of oscillation, because they are pretty sensitive to these variations, right. So, passive parameters are made stable in their value. They are selected in such a manner that these values do not change with temperature or time. So, that the frequency does not change with temperature or time. That is one aspect of frequency stability. Whether it is RC oscillator or LC oscillator, the performance is the same in terms of passive parameter sensitivity. Is the same. What it means is, if I am designing a LC oscillator, right, the capacitor I put should be more dominant than the parasitic capacitor, okay, so that the frequency stability of my circuit is good, or the inductor I put, okay, in my design should be greater than any lead inductance in order that the stability of oscillator is good. Okay. So, this is illustrated in the crystal situation also. The parasitic normally comes as a shunt capacitor, and the sensitivity to shunt capacitor should be very low. That is one aspect. Next aspect is, this is different, active parameter sensitivity. In realizing these oscillators, we had used op amps, okay, transistors, etc. What is active parameter sensitivity? It is the same thing. Is omega naught sensitive to, let us say, the parameter, active parameter of the device that you are using. Let us say beta of the transistor. For example, one active parameter is beta of the transistor, okay, or GM of the transistor. These are all active parameters. Okay. In the case of these are for the transistors, FET and this thing. For and also input resistance, output resistance. These are all, okay, the parameters which will influence, okay, the in fact, I should not put input resistance, I should put as input impedance, okay, output impedance. These are parameters which will affect the performance of the oscillators. Similarly, in the case of op amp, A naught, open loop gain, okay, and actually A naught also depends upon frequency. Let us say this is called the bandwidth, let us say dominant pole. We will discuss this later. It has a frequency dependence. The gain has a frequency dependence. So, its frequency dependence. Again, input impedance, output impedance. These are the parameters which are responsible for changing this. If the frequency is dependent upon these parameters, then these parameters in turn will depend upon supply voltage, temperature, okay, and the device itself. When I change the device, these may change because these properties are different for the other device. So, the stability of such oscillator which is designed using these components is now poor if the dependence is heavy. If the dependence is not so heavy, the stability is good. Now, how does stability come into picture in oscillators? This part we will discuss now. In any oscillator, we have seen that we have discussed it in terms of two things. One is the loop gain, this is the loop gain. Okay. The loop gain becomes equal to 1. This is both in phase as well as magnitude, right. That is, there is no phase, okay, 0 phase, and the magnitude becomes equal to 1 at a certain frequency omega equal to omega naught. Then it oscillates. This is what we have shown. At that frequency it oscillates. This is the basic principle. Now, let us consider this. I am for illustration taking Wien bridge oscillator, so that you can understand this clearly. We had put here resistances, let us say R A and R B. The gain was 1 plus R B by R A, and we had put here resistors. Okay. In fact, it could be just R 1 C 1, R 2 C 2. Right. You remember this? Then we had closed this loop. So, this was our Wien bridge oscillator, and we had got some condition for oscillation, etc. We again derive that 1 plus, if this is V I, we just said this is 1 plus, I break this loop here, this is V I, this is 1 plus R B by R A times V I. Okay. That multiplied by, this is how we had derived, let us say Z 1 by Z 1 plus Z 2 is the voltage here, and I divided by Z 1 plus Z 2 y 1 it became, and then we consider this as Z 2 is R 2 plus 1 by S C 2, and Z 1 is 1 over R 1 plus S C 1, and we just wrote this as 1 plus R B by R A, okay, V I by 1 plus R 2 by R 1 C 1 by C 2 plus 1 over S C 2 R 1 plus S C 1 R 2. This was frequency dependent, okay, and this was, I brought out the J here, let us say this became minus omega and this became plus omega. So, essentially we had this going to 0 at omega naught equal to 1 over C 1 C 2 R 1 R 2. This was vanishing, and we made R B by R A, that was the condition for oscillation, equal to R 2 by R 1 plus C 1 by C 2. You remember this, and we made it all equal, R B by R A equal to, okay, R 2 by R 1 equal to 1, C 1 by C 2 equal to 1, R B by R A equal to 2. When R 1 equals to R 2, C 1 equal to C 2, this was R, this was C, and therefore, this was omega naught squared, this was C squared R squared. So, omega naught was 1 over C R. This I am just repeating for completion's sake. Now, what is active parameter sensitivity? Passive parameter sensitivity is clear. What is active parameter sensitivity? The gain here is finite, let us say A. If that is the case, it is not infinite. I am considering only one aspect here. The gain is not infinite. We are not considering input impedance, output impedance, that will further add to our trouble, right, because output impedance will add in series with R 2, okay, and input impedance will add in shunt with R A. So, definitely if input impedance and output impedance become comparable to R A and R 2, right, it is going to cause stability problems. In this case, we will not consider that, we will consider only the gain aspect and show. Okay. So, if this is A, we had earlier derived that the gain is not this, okay. The gain is A divided by 1 plus A into R 1 R A by R A plus R B. Do you remember this? For the non-inverting amplifier, we had derived this gain when it is not infinite, A by 1 plus A into beta, beta being R A by R A plus R B. So, actually speaking, we will divide it by A beta throughout. So, the gain is really 1 plus R B by R A, which is correct, divided by 1 plus 1 over A beta. A beta is considered as the loop gain for this, right. So, the loop gain A into beta, it can be rewritten this way, that is the error. Okay, it will, if A is real and equal to A naught, there is no problem. It is less than 1 plus R B by A R A by certain amount. I have to make R B by R A slightly higher than 1. Okay. Still frequency stability is not going to be disturbed. Is this clear? If A is real, this will be simply A naught, and this whole factor has to be made equal to, let us say 2, that is this whole factor has to be made equal to 1. Okay. R B by R A should be close to 2, but slightly higher than 2, that is all that has to be done. So, this whole factor should be made equal to 1 plus, let us say, R 2 by R 1 plus C 1 by C 2. Okay. This is the condition, and therefore, if A naught is not infinite, there is no problem of satisfying this condition. It is not coming into picture in the frequency of oscillation, nothing comes into picture as far as A naught is concerned. But if A naught is also frequency dependent, then there is a problem. Let us say A naught, A is frequency dependent and it is A naught by 1 plus S by omega d, as we have put. If this amplifier gain is frequency dependent, then we will see that this A naught divided by N plus d. Now, this is not the case, this is not the real part at all, because this is also contributing to phase shift. Do you see that? That means, this was purely real from here to here, earlier it was purely real, either it was 1 plus R B by R A or 1 plus R B by R A divided by 1 plus 1 over loop gain, okay, as long as the loop gain was real. But now, the loop gain is contributing to a phase shift. The whole thing therefore, okay, says that the output is not exactly in phase with input. This is not an exact non-inverting amplifier, there is an error. To that extent, earlier from here to here the phase was 0, and therefore, at the frequency omega naught we could just make the phase equal to 0 for this network also. So, it was oscillating with output being equal to input or loop gain being equal to 1. So, I could close this exactly. But now, what happens? Let us say there is a phase error, phase lag of 1 radian. I mean, I am just giving it as an example. At the frequency of interest to me, it is giving as much phase shift as 1 radian, let us say. That depends upon the omega d, 1 radian. Then the frequency at which I should select this network is not omega naught any longer, it should be deviating from omega naught that such that it will give a phase lead of 1 radian. So, the phase shift of this should be such that it will give you a phase lead, that means it will be different from omega naught. How much it is going to be different is going to depend upon this phase shift here, right. So, we have to study the phase variation of this network, passive network Z1 by Z1 plus Z2 in order to say how much it should be different from omega naught in order to give a phase contribution of 1 radian, okay, phase lead. So, that the phase lag there by the active device is compensated for by the phase lead here. Suppose that I compensate, okay, at certain frequency, and for 1 degree it gives you the frequency of oscillation slightly different from omega naught, okay, so as to give a phase lead of 1 degree. Next it will change to 1.5 degrees because of temperature variation, then this will change correspondingly to a phase lead of 1.5, that means the frequency has to change again. So, now you see how frequency of oscillation of this Wien bridge oscillator is directly dependent upon, okay, the frequency, that is variation, and the phase variation with respect to frequency here. So, let us plot the phase variation of this network with frequency. If you plot that, you can see that this part of the network gives you this kind of thing, 1 plus 1 R2 over R1 C1 over C2 plus J into omega C1 R2 minus omega C2 R1. This is the expression. R2 is equal to R1 nominally. So, we will consider the nominal values. R2 is always made equal to R1. So, this is equal to 3. So, this is C, this is R, this is the condition. You will see that at omega equal to 1 over CR, at omega equal to 1 over CR, this phase is 0, it is just 1 over 3, right. So, at omega equal to 1 over CR, which we are calling as omega naught. This is not the actual frequency of oscillation, this is the theoretical frequency of oscillation at omega naught. The phase is 0, let us say phi is 0 here. At very low frequencies, just consider it at very low frequencies, this is going to 0, this is going to become very huge. So, it is only the contribution due to this. This is minus 1 over minus j or plus j. That means, it will give you a phase shift of 90 degrees. At very low frequencies, it gives you a phase shift of 90 degrees. At very high frequencies, this goes, this becomes dominant, this becomes negligible. So, at very high frequencies, this gives you a phase shift of minus 90 degrees. So, it is going to change in this manner. How it changes at this point is important. Now, you can see if this 90 degree is lag, this 90 degree is lead. That means, if it has to contribute to lead angle, then the frequency fixed by this network should be less than omega naught, which is 1 over CR. So, obviously, if an amplifier network is giving you lag, this frequency at which this is going to give lead is going to be less than omega naught. That is invariably the case. By how much it is going to be less depends upon the phase that you want, lead that you want to give to compensate for the phase lag that it has suffered through the active device. How much it is going to deviate here depends upon the slope here. That means, delta phi by delta omega is an important fact, because this is one curve, another curve may look like this, another curve may look like this. Let us now see this curve. If delta phi by delta omega is very high, omega oscillation, actual oscillation will be very close to omega naught, irrespective of the phase lag contributed by my active device. This is an important aspect. That means, if this is a steep thing like this, then the frequency stability is good. If the passive network can give a steep thing, whereas in the case of passive RC network, this you can find out for this phi is minus tan inverse omega CR minus 1 by omega CR just divided by 3, right. So, this is the phi. So, you can differentiate and find the maximum at omega equal to 1 over CR, and you will find that this quantity is not much for any passive network for that matter. Okay. Whether it is phase shift or Wien bridge, you can always find out delta phi by delta omega, it is not going to be much. Whereas, in the case of a crystal or an LC oscillator, okay, this is going to be pretty high. It is directly proportional to Q, and Q for the passive RC network, okay, is never greater than half. Okay. That means, all the poles of these passive networks always lie on the negative real axis. You cannot get complex conjugate pair of poles, and you can prove that Q cannot be greater than half. Okay. Whereas, in the case of LC network and crystal, Q can be pretty high. Complex conjugate pair of poles will occur, okay, and this pair of poles can be very close to the imaginary axis. Okay. If they are very close to the imaginary axis, the resonance frequency is close to the actual frequency of oscillation, and therefore, the phase shift variation is directly proportional to Q. The higher the Q, the steeper is the phase variation, right? And that is why frequency stability of any oscillator directly depends upon the Q quality factor of the passive network that composes the frequency determining network. Okay. So, irrespective of the device that you use, in the case of crystal, apart from the phase varying so rapidly, even the magnitude of the impedance goes from 0 to infinity. So, this facilitates, okay, the crystal being used in the loop, okay, and invariably the crystal oscillator oscillating at the crystal frequency, right. At any temperature or any situation, okay, extreme situation, the crystal still makes the oscillator, okay, oscillate at the crystal frequency, as long as what, the loop gain is greater than 1 in magnitude, okay, at that has to be provided by the active device. At all temperatures, if this is satisfied, that is enough, okay, but the phase part of it is automatically getting satisfied. Even the magnitude part is going to be somewhat getting satisfied, because the impedance value itself changes in the case of a crystal. So, this is an important aspect of frequency stability. In order to understand what we have discussed so far in terms of frequency stability, let us try to solve this problem. This problem will also illustrate a typical situation of an amplifier used with LC oscillator or a crystal. Okay. The crystal can be connected here or in place of this 100K, and the 100K can be put there. That kind of illustration we can do. Okay. Ultimately, at resonance, this LC network will act as a pure resistance 100K, okay, and that frequency omega naught is going to be 1 over root L into C. L is 10 to power minus 3. This is the value of L, and C is, okay, 10 to power minus 7, 100 nanofarads. Okay. So, that is C. So, that is going to be therefore equal to 10 to power 5 radians per second. That is the resonant frequency, okay, which is equal to 15.9 kilohertz. That is the frequency of oscillation, I say, because at that frequency of resonance, this whole thing resonates, and this will act as a 100K resistance, and from here to here the attenuation is half, 100K divided by 100K plus 100K. So, half. So, output voltage will be same as input voltage. If I make RB equal to RA equal to 1, RB by RA equal to 1, then the gain is going to be 2 from here. So, attenuation half. So, this is the condition for oscillation. This gain is 1 plus RB by RA, and this into the effective attenuation here is nothing but Z divided by Z plus 100K. This is the effective attenuation. This impedance we will call it as Z, and that is the loop gain from here to here 1 plus Rb by Ra into Z by Z plus 100 k is the loop gain if I break the loop here. Okay. So, this is the loop gain. So, this has to be, I close this, that means it is made equal to 1. So, 1 plus Rb by Ra into 1 by 1 plus 100 k, that is 10 to the power 5 into y. Y is the inverse of z, 1 over z. Okay. That is nothing but 1 over 10 to the power 5. Okay. This is the resistance 1 over 10 to the power 5, conductance of that, plus S c plus S c. C is really equal to 10 to the power minus 9, okay, plus 1 over S L. L is 10 to the power minus 3. So, that is the transfer function, okay, composite transfer function. So, we will take this inside where this S c is 10 to the power minus 7, it is 100 nanofarads. Yes, thank you. So, we take this inside, this is going to be loop gain. Now, we would like to write it in general for a finite value of A. That means, 1 plus Rb by Ra gets modified, we have seen in the lecture that it will get modified as 1 by 1 plus 1 over loop gain, that is 1 over A into beta, beta being equal to Ra by Ra plus Rb. So, this if A is infinity, this will be 0, okay. Otherwise, this is the composite loop gain. This has to be equal to 1 for oscillation to take place. Now, what it means is 1 plus Rb by Ra divided by 1 plus A. A is 1 over A naught plus S by omega d, that is what, say A naught by 1 plus S by omega d, that is how we have taken. So, A naught is in this case 10 to the power 6 and omega d is 10, okay. That into Ra by Ra plus Rb. We can take the nominal value here, Ra by Ra plus Rb is very close to half, we have chosen, right, because this is going to be still very close to half. So, we will take this nominal value in this case, and this is going to be how much? Half, that means this factor will be 2. This is Ra by Ra plus Rb is half, okay, nominally. It is not exactly now, okay, it will be exactly half only when A is infinity, right. Now, it will be less than half. So, that the gain, overall gain is slightly greater than 2. So, to that extent what value of Rb by Ra we should get, we will come to know from this expression, right. So, this is an approximation, okay, to a certain extent into 1 plus 10 to the power 5 by 10 to the power 5, that is 1, okay, plus S into 10 to the power minus 2 plus 1 over S into 10 to the power 8. So, this is equal to 1 plus Rb by Ra. Once again I say that Rb by Ra we have taken as equal to 1, okay, only in the non-ideality. It will be close to 1, but will be different, that value is going to be fixed by this. So, this is a factor of 2, that factor 2 you take out, this 2, okay. So, it gets normalized now 1 plus okay, s into 10 to the power minus 2 divided by 2. We have taken out 2 here. Okay, this is nothing but 2. That 2 we have taken out. 10 to the power 8 by 2 s. So, this is the expression. Now, you can see that this loop gain has to become equal to 1. Okay. Now, actually speaking, I think I removed this. Where is that? There is this factor, this into 1 plus, okay. What is that? 2 into 1 plus s by 10 divided by 10 to the power 6. So, now you can see that the phase shift is governed by this factor here. This is the active parameter phase shift. Okay. This is contributing to active parameter phase shift, and that is going to be very little because there is a 10 to the power 6 factor coming here. Okay. And therefore, we can evaluate this. Now, you can see that if this is not contributing to anything, R b by R a should be made equal to 1. So, that this 2 get cancelled. So, the loop gain becomes in magnitude equal to 1, and the frequency is determined by this factor. This is j omega and this is minus j by omega. So, these factors equated will give you the frequency omega naught as 10 to the power 5 radians. Is this clear? So, we will see that it really depends upon a Q factor coming here. I have earlier in the case of filters explained to you how to normalize this whole thing, right. So, that we get this as, now I can multiply this, there is a 2s factor here, this factor has to be made equal to 1. Okay. That means, I multiply the whole thing by 2s by 10 to the power 8. Okay. So, that means, this factor becomes equal to 1. Okay. This factor becomes equal to 2s by 10 to the power 8. Okay. And this 2s means s squared by 10 to the power 8. Okay. Is it correct? 2s. Okay. So, 2 gets cancelled, and 10 to the power 8 here you get this as 10 to the power minus 10. So, this whole thing simplifies to, in the denominator, okay, this is going to be neatly written as 1 plus R b by R a into 2s by 10 to the power 8 divided by 2 1 plus 2s by 10 to the power 8 plus s squared into 10 to the power minus 10. And we said the coefficient of s squared here is going to be 1 over omega naught squared, which is called the resonant frequency in the case of filters. Okay. So, you can see that 1 over omega naught squared is 10 to the power minus 10. So, 1 over omega naught squared is equal to 10 to the power minus 10, or omega naught is equal to 10 to the power 5, which we have got. So, we will write it as s squared by 10 to the power 5 squared. This is s squared by omega naught squared. Okay. So, here we have to have s by omega naught for normalizing. S by omega naught means s by 10 to the power 5. Apart from that, we will have 10 to the power 3. And this factor 2 by 1000 is going to be written as 1 by 500, which we have earlier defined in our filters as Q factor of the pole Q, if you remember. So, here the pole Q is equal to 500. Okay. So, pole Q is 500, resonant frequency is 10 to power 5 and this is the normalization. So, this LC network has a pole Q of 100, 500, it is a pretty high value. That means, the variation in phase here, okay, with respect to frequency delta phi by delta omega in this case is going to be around omega equal to omega naught is directly proportional to 500. It is a huge quantity, right. How do I really determine that? Right? You can now find out the phase of this network, okay. Phase variation here. This contributes to a constant phase of 90 degree here, right. This only contributes to a phase, okay. This is going to be 1 by 500 into omega by 10 to power 5 divided by 1 minus omega squared by 10 to power 5 squared. Okay. This is tan inverse of this is the phase contribution due to the pole imaginary part, okay, divided by the real part. Imaginary part put S is equal to j omega. So, omega by 10 to power 5 into 1 over 500, that is the j omega part. 1 without j omega, real part is 1 minus omega squared by 10 to power 10, 1 minus omega squared by 10 to power 10. So, the real part divided by imaginary part, tan inverse of that, okay, is the phase. Is this clear? So, now I am going to make an approximation here, okay, and show I want to establish only that at very close to omega equal to omega naught, very close to omega equal to omega naught, I would like to find out the slope. So, instead of differentiating, okay, we will adopt this procedure. At omega very close to omega naught, okay, omega minus omega naught, I will take it as change from omega naught, and omega plus omega naught, okay, is going to be twice omega naught. This is the approximation. At omega very close to omega naught, omega minus omega naught is delta omega, okay, that change. Omega plus omega naught is twice omega naught. If you do that, this 1 minus x squared, okay, is 1 plus x into 1 minus x. So, this denominator can be put as 1 minus omega by 10 to power 5 by 1 plus omega by 10 to power 5, right. So, this quantity is equal to 2 at omega very close to omega naught, this quantity is equal to 2. This quantity is 1 minus, okay, omega plus omega naught or omega minus omega naught, okay, omega plus delta omega we can put, omega plus delta omega or omega minus delta omega, that means this is delta omega by 10 to power 5, right. So, this 10 to power 5 gets cancelled with this 10 to power 5, we get this phi as tan inverse, okay, omega by, okay, 1000. This is important, you can see that the Q factor will come in the denominator of this, right, 1 by 1000, okay, omega by delta omega. Is this clear? From this we can see that delta omega tending towards 0, that omega equal to omega naught, okay, this is going towards infinity, that means phi is equal to pi by 2, that is the phase shift contributed by the pole. Phase shift contributed by the 0 remains constant at pi by 2. So, overall phase shift is 0. Okay. So, phase shift contributed by the pole alone is pi by 2, okay, at omega equal to omega naught. As omega changes from omega naught, it keeps changing, right. We would like to know how much it is changing from pi by 2. Okay. So, we will put this as, okay, delta theta, okay, plus pi by 2. It is going to change to some phi. Okay. So, this phi is going to be put as around pi by 2. So, how much it is going to be different from pi by 2 is going to be given by this delta theta, right. The phase is going to change from pi by 2. At omega equal to omega naught, it is pi by 2. Okay. So, if I put that, this is going to be delta theta plus pi by 2. So, I take tan. So, tan pi by 2 plus delta theta equals omega divided by 1000 delta omega. So, delta theta being very small, we are close to omega naught. So, this is equal to cotangent delta theta, which is cos delta theta divided by sin delta theta. Delta theta is very small, and therefore, cos delta theta is 1 and sin delta theta is delta theta itself. So, from this expression you get delta theta, the change in phase for a change in frequency around omega naught, this is important, equals 1000 divided by omega. This is important. In this 1000, q of 500 is there. So, it is really equal to 2 into 500 by omega naught, because we are substituting omega equal to omega naught. So, this is nothing but 2q by omega naught. This is an important expression. For any such circuit with pole q equal to q, the change in phase with respect to frequency is equal to 2q by omega naught. This can be done by regular mathematics, by finding out the delta phi by delta omega straight away. Instead, by approximation you can do it this way also, 2q by omega naught. So, this is very steep variation of frequency with omega naught. Now, if you consider the whole expression at omega equal to omega naught, this expression is going to contribute to 0 phase shift, but there is going to be a phase lag contributed by this gain, finite gain, and therefore, this is 1 plus 2 divided by 10 to the power 6. So, that 1 plus 2 by 10 to the power 6 can be ignored. So, this can be ignored compared to this. So, it is 2 s by 10 to the power 7. That is going to remain here. So, if you put s is equal to omega j omega, this is going to contribute to a phase additional phase lag of at that frequency. The additional phase lag will be 2 omega naught by 10 to the power 7. It's that being very small angle, you can say that tan inverse of that is that angle itself, right. So, 2 omega naught by 10 to the power 7 is the additional phase error. So, to that extent this will have to contribute, and that can be done by that changing very little from omega naught. So, this phase error can be compensated by this slope here. The slope is directly proportional to q, and therefore, because q is very high, the omega has to change very little from omega naught in order to accommodate this phase error. Is this clear? So, you will just equate this to this phase error, and therefore, you will see that the actual phase frequency that is going to be different is going to be different from omega naught by a factor which is determined by q, 1 over q of this factor, right. So, this is the phase error. This has to be compensated for by delta phi by delta omega, by delta omega changing accordingly from omega naught. Delta phi by delta omega is 2q by omega naught. That means, this into delta omega. So, delta phi is 2 omega naught divided by 10 to power 7. That is the phase error. Okay. And what should be the delta omega? That delta omega is given by 2 omega naught squared by 10 to power 7 divided by 2 q. So, you will see that q always comes in the denominator, right. So, the delta omega which has to be different now becomes very small. In this particular case, you can now substitute what? Omega naught and c, 2 into 10 to power 10 divided by 10 to power 7 into 1000, 10 to power 3, is it 1000, isn't it? So, this is the 2 what is that, radians per second. Omega naught is 10 to power 5 radians per second. So, this much deviation can be accommodated by frequency of oscillation changing only by 2 radians per second. So, we have solved the problem as well as made you understand what is frequency stability.